So the question on the table is, if you see something like this, should you think about it like tangent theta equals -1? And that's okay if you remember that it's not a tangent theta. And a tangent theta would be defined on an infinite number of angles, wouldn't it? Because the thing just keeps going and keeps going and keeps going. So if you want to think like that, to go, oh, it's a unit circle value, right? And it's -1 there and there. So you get that kind of thinking going, that's fine. But you got to remember, because it started inverse tan, you have a built-in limit of -π to π2, or -90 to 90. So of those angles, there's no way that one can work, right? And that one, which you normally would probably call 315, can't call it 315, because 315 is much bigger than 90, isn't it? So you got to find a way to squeeze it in between -90 and 90, so you're going to rename it -45. Does that make sense? And you, same thing with a regular tangent. I know that on this quiz you just took, right here, to solve this problem, you changed it to an inverse cotangent, right? To solve this one, you changed it to an inverse cosine. But because it started cosine, I didn't use that 0 to 180. Are you with me? Even though I did this, and notice my calculator only spit out one answer. Your calculator knows. It knows there's only one, and it'll give that to you. But because I started with a cosine, I got to assume everything works, unless they give me a number, which they did. That limited me a little bit. But with the trig function given, I would have to limit it for you to have a certain number of answers. But with an inverse trig function, you are always limited by that predefined limit because of where the graph shows up. And you don't have to know where the inverse functions, how to graph them. But remember we talked about it? I don't remember if y'all were here or away, but we talked about why it had those limits, because it had to pass the vertical line test. So you just got to memorize those limits. So when you're doing any of these, like all of these trig function problems right here, right there, it's a trig function, not an inverse. So no defined limit, find the angles and keep adding 360s or subtracting 360s. Trig function, find those. Now if it gives you a limit, then limit it. Trig function, if it gives you a limit, limit it. But inverse, and then same thing with 10A, B, and 11A. But on starting with the inverses, it didn't give you a limit. So you have to know, you're welcome to think this way. I probably did the same thing at one point. Now I don't really, because it's kind of synonymous in my head. But right there, I have to come up with that. Inverse sine, I've got to know that. And I don't know why I went pi/2 and then 90 here. Same difference, whatever. I know most of you deal in degrees. I'm subtly trying to wean you off of that, because next year we don't do any degrees. Like temperature, maybe, but nothing else. It's all radians. All right, and we'll talk more about that when you get there. And then right here, inverse cosine, you're welcome to think that way, but it's 0 to 180. You have to remember that. Every year, people just get smoked on that section because they write this, and then they write two answers. And I'm like, dude, it's not tangent, it's inverse tangent. It's a different graph, right? So anyway, you've got to break through on that. If that still didn't make sense, come see me. I can break through. I just have to maybe understand how your brain's thinking, you know? And I know some of you kind of get it, and some of you are like, I don't get it, but I'm not going to say a word. I don't want to look stupid. I'm the same way. I'm not that guy like in groups that's like, what? I'm the guy that's like, so I get it. Just come talk to me if you really want to get that straight if you're struggling. Anybody else on any of this? Composite stuff? Sometimes that's hit or miss.
Why is number 13 not 200?
Why isn't it not what?
200.
Right here, what do you see? Inverse sine? Is inverse sine defined? Where? -90 to 90. So like when I'm looking at this right here, if you got to that, or did you just cancel it?
Well, like, why couldn't you just cancel it? Oh, because it's, okay. Yeah.
Right?
Yeah.
And you don't get in the habit of thinking that. I mean, I can tell you this. Do you remember the intervals that you wrote down? You said, hey, remember I gave you this, the inverse sine of, I don't remember how I worded it. on one of your worksheets, it said something like y equals inverse sine of x. And I said, what do the values have to be in between? And I said, what do the angles have to be in between? Do you remember that? And what is x, a value or an angle? And that's a big deal that you know that. Because remember, you trig function angles, but you inverse trig function values. So this must be a value. And we know that my values have to be between what and what? Negative 1 and 1. And that has to do with the hypotenuse is on the bottom of the definition, and the hypotenuse is always the biggest. So it keeps that fraction between negative 1 and 1. And then what do the angles have to be between on inverse sine? Negative 90 and 90. So if both of those things are true, like if you ever look at an inverse sine or a sine, or an inverse tan of a tan, or a sine of an inverse sine, if the angles are between negative 90 and 90, which they're not, or the value is between negative 1 and 1, which it's not, but if it was, then you can cancel. If you want to remember that. Now you're going to have to remember that's different for cosine, right? On cosine, the angle's going to have to be between 0 and 180, and the value's there. And on tangent, the value could be anything, but the angle has to be between negative 90 and 90. But if that's true, then you can't cancel them. But if it's not, no, you got to just slowly go through it. That of that's negative a half, and then you go, all right, where would sine, inverse sine, have a value of negative a half? Down a little, 210 or 330. Oh wait, inverse sine. It's got to be there. Negative 90 to 90. But that's way bigger than a 90, right? You had to go all the way past 90 to get to there. But not if you go this way. If I go this way, though, it's negative 30. You can get this. I know it's a lot to throw out. The upside is we're not going to build on this anymore. We're going to do graphing trig functions, and most people like graphing trig functions. You guys probably loved them last year because you had all your notes out. But we got to get better this year. So last year I used to go through all the graphing trig functions in one day in this class. And then we did one more day of going from the graph to the equations, but this year I'm going to spread it out into 2 days. Okay? So I'm going to slow it down so that you can get it. All right? Because I recognize that I'm going to have to do that on stuff that we didn't do a great job of. That you may not have done a great job of at home, which I totally understand. I am a human being. If I was given that opportunity, I would have opened notes the crap out of it too. So, anyway, I want to jump to something different, but any last questions on the quiz? Because your test it'll look like partially this and partially the graphing trig stuff. Okay? And there's only a couple things that are tricky to me on the graphing trig stuff that traditionally that I remember people having issues with. And you might or might not remember them when they come, but I will definitely point them out. All right? Thumbs up? Whatever, something, huh? Okay, so move off of this, and we're going to the graphing trig stuff. And so we're going to our book. And let's jump to page. I have a feeling it's not this, but it is not. Keep adding stuff. Need to update this.
I think it's 113.
113? Yes. Okay, page 113. And our book keeps growing. It was 103 last year. Added 10 more pages of stuff. All right, so let's check it out. Graphing trig functions. Now, there's a whole lot about, and we're going to do sine, cosine, and maybe start getting into tangent. And be happy because normally I do sine through cosecant all in one day, and boom, we're done. So, slowing it down a little bit, you're probably going to remember some of this. But a trig function could be very simple, like just sine x. You're not going to see that. You're going to see, on your test, something like this. All right, now at first glance it looks pretty ugly, but basically there's your sine of x. Stuff where you're adding to the outside of the function, what does that normally do? Shifts it up or down. Now normally you see stuff like x squared and then a plus 2 on the right. But for trig functions, for some reason, and logs, they like to put the plus 2 or whatever to the left, so it doesn't look like it's part of this parentheses. Because sometimes people are sloppy. Like for instance, if I wrote y equals sine of x plus 2, some people, especially when they're early, they think of it like that. Are you with me? So to avoid that confusion, they usually write, when it's a shift upward, they usually write it out front. Okay? So that's not like you've been used to seeing stuff when we're talking about shifts and reflections, but that should be the same. D, vertical shift. That's us shifting the entire graph up from the x-axis or down from the x-axis. Okay? And you already know about shifts. Now, it is a little bit different that you have not, remember parabolas, for instance? You might have a number out front, a number on the inside added or subtracted, and then maybe something like this. But what you didn't have was a number inside the parentheses with that x, did you? And because it wasn't in good parabolic form. But in trig form, you will have that occasionally. And you're not going to overly worry about it. But what that means is this c value, unlike that 1, isn't the shift. The shift is that over that. Or even better, I'm going to go right here to phase shift. If you just take the bx minus c and set it equal to 0 and solve, so you basically change the sign of the c, whatever it is, move it over, divide by 2. So set it equal to 0 and solve, that's going to tell you what we call the phase shift. That's this shift, left and right. Which makes sense. If it's negative, you're going to be going to the right. If it's positive, you're going to go to the left. But it's not just c. Are you with me on that? Okay, so that's a little bit different than this, only because there's going to be a number occasionally in front of that x. And then the a value, what did that 2 do on a parabola? What would that 2 do to it? It stretches it up? Well, that's what it does if it's in front of the sign. It just takes the sine curve, and instead of going up to 1 and down to -1, it just stretches it more. Makes it taller up and taller down. So for a tangent graph, if a tangent looked like this and you had a 3 in front of the tangent, it's just going to make it steeper. But it's not going to make the period any longer or anything like that. It just makes it go up more and then down more. Y'all with me? So that's the A. And why did I put it in parentheses? Well, sometimes it's like a -5 sign or a +5 sign. But the negative doesn't affect how much it goes up and down. It just affects whether the graph starts up or starts down. We'll talk about that in a second too. Yeah.
So like a regular graph.
What do you mean by regular?
Just one with.
Like a parabola or something, or?
I guess so. Just like one of the 12 that we learned.
Okay.
The basic ones. When you like add something to x, it goes to the left, and minus x, it goes to the right.
Correct. And that's still true here.
That's still true for this. That's what
Yeah, the sign part's still true. But what's not true is like this right here says I'm going to the right one. But if I had this in there, this would not mean that I'm going to the right one. This would mean I'm actually going to the right 1/3. But nobody's ever written it like this before because that's not good trig form. I mean, that's not good parabola form, is it? So we would never have simplified it to this. But that's what I would have done. Well, I'm just saying that's what you're going to do on a trig function when you have this, this bx minus c. So you're going to take that, you're going to put it over the b, and you're going to change the sign to see where I go. So it's the change the sign part's the same, but remember to put it over b. And I'm just saying the easiest way I know people to do that is just set that part equal to 0 and solve. And if it's negative, you'll get a positive number, and you'll go to the right. If it's positive, you get a negative number, and you'll go to the left. And you'll just mark that vertical axis. And that's not an asymptote, that vertical line there. And that'll give you that new y-axis. Are y'all with me? So, shift up and down is the A. I'm sorry, is the D. Sorry, it looked like an A there. Shift up and down is the D. The amplitude or the stretch, I called it the height above or below the vertical shift. So once I've shifted up my x-axis, the amplitude marks the amount above or below. Kind of gives you kind of your ceiling and your floor on sine curves, not on tangent curves, but on sine and cosine curves. And then the final thing is the period. And do you remember what a period is? In math, where like a sine curve could do a complete cycle in this much, it could do a complete cycle in this much. It could do a complete cycle in this much. Well, that's going to be found, that length of that period is going to be found, that's the last thing we're going to look at. And the definition for the period is 2 pi over the b. So the b value, if you look back, is whatever's in front of the x. So if you take 2 pi, and the reason why it's 2 pi is that 2 pi is 360, it takes 360 degrees to complete a cycle on a regular simple sine curve. But as I change that number, it changes the period. You know, like if I put a 2 there, it's going to put, when you put 2 pi over b, it's going to put it in 180 degrees as opposed to 360 degrees. If I put a half there, it's going to take me 4 pi. Instead of completing the cycle in 2 pi, it's going to complete the cycle in 4 pi. But you don't have to worry about trying to logically think through it. Just take 2 pi, put it over the b, and you'll have your length of your period. Now that is true, what I've just said, about all the sine and cosine graphs. So anything sine and cosine, that's going to be true. And then if you remember, and I'll go back through those tomorrow, well, Monday, the secant and the cosecant curves are all built off sine and cosine. So if you get sine and cosine down today, you're going to be in really good shape for secant and cosecant, because there's only like 2 things you do to to graph a secant curve. You basically graph the cosine and then do 2 things. So it's important that you get these down, but these rules are great for sine and cosine, and also for secant and cosecant, which we'll get to later. They change a little bit with tangent and cotangent, which we might play around with at the end of the day, but most of it's going to be done on Monday. Are you with me so far? Now, the other thing that you're just going to have to learn is what the general sine and cosine graphs look like. And then we'll put all this together. So a general sine curve, and I'll show you why once, and then I'm not going to show you why on all these, but a general sine curve is me just plotting values. Me just finding angles and plugging them in there. But I hate doing this. It takes so long. Like for instance, if I made a chart for X and Y, okay? So I am not going to do this ever. I'm going to know the patterns here. But if I've started plugging in angles in there, and what angles would you like to plug in since you don't really, pretend you don't have a calculator? 0? Why not start at 0? And the sign of 0 is, and you go to unit circle, what's the sign over here? Up, nothing? 0. There's my point. What's another great angle to plug in? Pi over 2. I love pi over 2, but we know even more than that, right? Again, I'm only going to do this once, but how about pi over 6? That's 30 degrees. That's the next one up on the unit circle. So pi over 6, or 30. And if this is pi, if you broke this into 6 parts, this would be pi over 6, right? Now, what's sine at pi over 6? Up what? Over a lot? Up a little, so up a half. So right there, I'm going to go up 1/2. You follow me? Now, what's the next one up from pi over 6? Pi over 4. Now, what's pi over 4 when I take the sine of it? Or 45. Root 2 over 2. Now, root 2 over 2 happens to be about 0.7, if you were to type that in your calculator. So it is root 2 over 2, but that's about 0.7. So I'm going to go, all right, pi over 4 would be right in the middle, maybe 0.7-ish. What's the next one from pi over 4? Again, you do not have to do this. What? Pi over 3. Pi over 3 is like 60 degrees. What's sine of 60 degrees? Root 3 over 2. And what do you, root 3 over 2 is about 0.86-ish. So between 0.8 and 0.9. So pi over 3 is right there, maybe 0.8, 0.9. And then what's pi over 2? 1. So I go up to 1. So if you didn't have this curve, that's how you'd have to graph it. Except it'd be a whole lot worse than this, because it wouldn't be this simple. It would be something like 3 minus sine of 4x minus blah, blah, blah. And you'd have to pick angles or values for x that actually gave you recognizable angles. It would be a disaster. So what I want to do is mark all my shifts and everything in there to figure out what it's going to look like. And then I'll just be graphing a simple sine x in that little box, I call it. And that's kind of what I did here. Now, if I kept going, do you have confidence that I would continue to get these angles? Or these, I'm sorry, if I plugged in these angles, I'd continue to get more values? And doesn't it make sense if you think about the unit circle? Where is sine positive? In which 2 quadrants? First and the second, which is all the way through 180. Look, through 180, positive values. What happens from 180 all the way down back to 360? Negative values. So this is basically a translation of your unit circle values to a graph. I do not want you to do this. Here's what I want you to do. I want you to look at this graph, And I want you to figure out what the shift is up and down. And I want you to mark that. Okay? Then I want you to take your amplitude and figure out how high or how low you go from that D value. And I want you to mark that. Then I want you to figure out where your phase shift is. This shift. That's the Bx minus C, set equals 0 and solve. Figure that out. Mark that. Wherever it is. And then I want you to find your period. Figure out how long that is, which that's a little tricky, but we'll talk about that. Because your ruler always changes. This is like a number line, it's like a ruler. Sometimes 2 pi will be there. Sometimes 2 pi will be here. So you have to think through a different scale, like a different measurement each time. But you mark the length of that period. And when you mark those things, what do you end up with? This little box thing. And if you can get this box, you're home free. As long as you know how to graph a basic sine. So a basic sine curve, if you have a box, bumps up in the first half, bumps down in the second half. A basic sine curve that's negative goes down first and then up. A basic cosine curve, same box, same information, so you're going to start it the same way, starts high and then goes down the bottom and then back up to the top. It always starts and finishes at the same height. You'll notice that. Same height. And then a negative cosine, instead of starting high and going down, starts low and goes up and then back down. Now your box is going to change size. So like for this sine curve, I can have this as a box. It might work out that way. But what do I do if it's a positive sign? I bump up first, then down. So you'd say, all right, there's it in the middle. It's going to have to go up and down. And that means it's going to hit up here, hit down here. Y'all see what I'm doing? That's like me saying, all right, cross is in the middle. And in the middle of that, it's up. Middle of that's down. And you mark these dots. And you go, all right, must do that. And then that. But sometimes your box is going to look like this after you label everything. Same thing, it's still one period in there. So you go, all right, if it's a positive sine curve, find the middle. It's got to be up like that, so halfway up, halfway down. And you mark those 5 dots, and you go bump up, bump down. But it's all about letting this information sketch you a box and then fitting one period into that box, however it looks. Is this kind of making sense? All right, so let's give it a shot. And guys, don't be afraid to say something. If you are struggling, I guarantee you somebody else is too. Oh, also, I realize that a lot of you like to take shortcuts. I do too. And I gotta be honest with you, I've probably given you most of the shortcuts. I'm not proud enough to suggest that there are no more shortcuts and better ways of doing it than I do it. But I would suggest if you find one, you run it by me, and then I can kind of confirm that it's good. I might learn something too. But I see people do this all the time. They get their box in there, right? And they're like, all right, you know, bump up, oh yeah, bump down. And they get it drawn poorly because they didn't put dots. Are you with me? And they didn't mark where things are going to happen. I had a kid once, I probably told you this in a video, but they were actually 2 brothers, Charlie and David Kwong. And one went to Duke and the other went to Georgia. And they were brilliant kids. But they had like some form of dysgraphia where they could not freaking, like, it was the worst handwriting ever. Actually, I got a couple of pretty bad. But like, this is one thing I noticed. And they were both like this, but like this was a 6, this was a 9, this was a 4. I was like, dude, like I had no idea what they're doing. And when we started graphing trig functions, it was it was horrible. I mean, so I was like, dude, that's when I came up with the dot system. I was like, just put the dots there so I have some kind of hope that I know that you know what you're doing. So they could actually get the dots in there. They'd be like, so they'd get their dots in there, and then it'd be like, you know, but I could at least look at it and like, okay, you can't control your pen, but I can tell that you knew where you wanted to go. And that was good enough. Are y'all with me? I always get somebody to smile. Anyway. But right here, make sure that you put the dots in, because if you do, and then you miss a dot, I'm like, okay, he's fine. Or she's fine. But if you don't, I'm like, Like if you don't have that in there, and you're just eyeballing it and winging it, you know, and you go, all right, I'm gonna come in there and I'm like, well, the dots should have been here, here. And I'm like, well, they missed all that. Now you're still gonna get most of your credit because you have the box drawn in there and everything, but the part about graphing it, you're not. But if you had all the dots in there, and then you're like, oh, I missed it, you know, I missed it. I'm gonna go, well, I knew that you knew where you were going, so it's okay. And by the way, don't do this either. Don't go, I put the dots in there. Okay, that's not showing me either. That's not helping. I want you to actually, and I normally do a pretty good job of making these things land on tick marks, so it's not hard. Occasionally you might have to go in the middle and come up, but normally there's enough tick marks to make it pretty easy for you to get your dots in the right spot. Are y'all good so far? Okay, let's see if we can put all this together. And again, I don't have to go anywhere near as fast as I normally do, so that should be a huge advantage. We should be able to do a lot of these. All right, and we're going to skip through all this stuff right now, and we're going to go to classwork examples. Okay, so this is on your page 117, and let's look at the sine and the cosine graph. All right, so remember, all sine curves, all cosine curves are graphed with the information you just learned. You with me? Okay, so what's this -2? It's out away from this function, only connected by addition or subtraction. What does it do? Shifts it either up or down, and because it's negative, down 2. So I know that it's hard to show a horizontal line on your graph unless you have like a thick pen. If you want to go bring out a marker or something to help you with that. What I normally do, if I'm trying to mark -2, I just try to put it right above or below so I can kind of see it. But this is my -2. And like I always do when I mark shifts, I'm just going to kind of scribble that out because it's not going to affect my graph any more than it just did. Next thing, what do I think you ought to do? And I would do it in this order. So I just marked the D value right here. Next, what's a good thing to do? I'm going to do the amplitude. And the amplitude, I'm going to ignore the negative. Don't even worry about that right now. It's the 4. That's why I called A absolute value of A. Ignore that thing. Just look at the 4. And what does 4 tell you to do? Stretch the graph. So I'm just going to stretch it up 4 and down 4 from what? From the D, not from the x-axis. The x-axis is, just ignore that from that one. So I'm going to go up A and down A from D. And I'm going to put dotted lines there. And there. And I'm kind of done with that 4, although I'm going to still have to look at that plus in a second. Next, what should I do? You can either do period or phase shift, but I would do phase shift first, and this is why. Although it doesn't matter, you can find it. But if you find the period, you really can't mark it because you don't know where you're beginning, can you? Or do you? So I'd rather know where I begin, and then when I find the period, I can mark it in there. So I'm going to find the phase shift, which is this shift. And by the way, you can do this shift or the A. Second and third, doesn't really matter. Okay? So I'm going to find that, and what was my hint to find out the left or right? I know it's going to the right, but what did I tell you ought to do? Set that equal to 0 and solve. So I have right now 4x minus pi over 2. I'm going to set it equal to 0, which gives me 4x equals pi over 2. And then what do you do now? You divide by 4. Now I have a question. When you divide by 4, does this bother you? Now a lot of people make a mistake. They see this and they cancel the 2 and they cancel the 4 and they get pi halves. That's not right. So here's my encouragement. You actually get pi over 8 here. And I think you'll see that more clearly if instead of dividing by 4, you just multiply by a 1/4. You see that? And then you won't make that careless error on canceling. So x equals pi over 8. Now, where is pi over 8 here? Pi over 8 means 1/8 of pi, right? Yes? And this is pi So if that's positive pi, I want to move 1/8 of the way to pi. Well, that would be what? 1/8, and look at how nice of me to break it up into 8 tick marks. So you're going to go to pi over 8, which is right here, dotted line. Now, do I always do it that nicely? Actually, pretty much. I'm not going to give you something that's marked off in 8s and then ask you to go to pi thirds, or that's marked off in thirds and say go to pi fourths. I used to, but I'm not doing that anymore. I'm trying to make it not about algebra and math and fractions, and more about just your knowledge. All right? So all I need to know now, I got the top, the bottom, and the middle, and the beginning of a period, or maybe the end of one. I need to know what? How long, this is the phase shift already, right? So this is my C over B, or my phase shift. All right, either one, depending on how you want to think about it. I need to know how long the period is. So how do I find out the length of the period? What is it? It's always, for sine, cosine, 2 pi over the b value. Now this is the part that, until you kind of get this down, is a little tricky for some. So pi over 2. Now remember, period is not a location. Period is a short way of me saying length of the period. Period's a length. So the length of the period is half of a pi. Now remember, the length of pi is going to vary from graph to graph. What is the length of this pi? You might remember me talking about this last year. 8 tick marks is the length of a pi. Are you with me? So half of a pi is how many tick marks? 4. So don't make the mistake of going, oh, my period is pi over 2. Go to pi over 2 and mark a period. No, do not do that. What I'm telling you to do is the length of the period is 4 ticks on this graph. Heck, it could be 8 on the next one. Could be 1 on the next one. But we're going to go 4 ticks from here. So 1, 2, 3, 4. That is 4 ticks, which is my period. Y'all with me? And that is the end and the beginning of the next. And I'm going to have you graph 2 on each of these. So I could do 1 there. Now if I do another one to the right, I'm off the graph. So why don't we just go 1, 2, 3, 4 back here. And you see the 2 boxes? That means each box has to have a separate period, a separate cycle in there. Now, I have taken care of everything now, everything but the positive sine of x. So, positive sine of x, what would a positive sine of x curve look like in your box? Bump up, bump down. So, if this is one box, I start here, I'm going to go up, back to the middle, and then down, back to the middle, which means I'm going to be high at the quarter and the low at the quarters. And those are my 5 dots. And then hopefully we have some kind of decent fluid motion, but even if you are Charlie and Jimmy Vonging it up, I will still see a nice little period. And then you're going to graph 2 of them. So again, bump up halfway, which means I'm up here, and then bump down the other half, which means I'm down there. 2 periods, and we're done. And here's the great thing. The setup for sine, cosine, secant, cosecant, all the same. So 4 of the 6, and then the tangent and the cotangent are similar. But for 4 of the 6, you're going to do these amplitudes, the phase shifts, everything is the same information. Capiche? All right, check it out. Let's look at number 2. Very similar, but this time what do we have? A negative cosine. Let's see if we can do that. Hopefully this one. Bring it home. All right, so first thing, what would you do? The what? The D, and that's a -1. So I am down here at -1. And that takes care of that. Next thing, what would you do? What would you do? You can really do phase shift or amplitudes. What do you want to do? Amplitude, that's the 3. Remember, you don't have to think -3 right now. You're doing 3, and what does 3 do for you? Up 3, down 3. More dotted lines. By the way, if you're looking at this and you're like, do I have to put the dotted lines in? I've got major skills. I can eyeball this. I'm going to be good. Again, I'm going to look at your graph. If your graph looks good, I'm fine with you not having anything labeled, unless it says to label it. But if your graph's off, I'm giving credit based on the labeling. So if you mess something up, I'm going, well, was their D in the right spot? Okay, that's worth something to me. Were their A's marked correctly from that D? That's worth something to me. So all those things are worth something. When you don't put them in there, you're not getting credit on the rubric that I have in my head for that problem. But if the problem's right, you're good. But I would go ahead and mark everything out there and get a nice box. Even if your graph's messed up, you'll get some credit for all that stuff. Next. Speak, young ones. Phase shift, how you doing that? So if I take that, set it equal to 0, I'm going to kind of skip a step. I'm going to subtract the pi over 2. And I'm going to multiply by 1/3 so I don't get a little canceling snafu. And I get negative pi over 6. What does that tell me to do? To go to the left 1/6 of pi. Oh man, too bad he didn't break it up into 6 little tick marks. Oh my gosh, look, he did. 6 ticks, right? 1, 2, 3, 4, 5, 6. So 1/6 of a pi is just this much, but I want to go to the left that much. So to the left, that's 1/6 of the pi. Y'all seeing that? Mark this. That's my phase shift. So I have my vertical shift, my amplitudes, my phase shift. I need one more thing to mark off the box, and that would be what? Length of the period, and the length of the period for sine and for cosine and for secant and cosecant is always 2 pi over the b. And the b in this case is 3. Now, let's be careful. How long is 2/3 of a pi? This is pi. 1/3 would be 2 tick marks, right? 2/3 would be 4 tick marks. So 4 tick marks is 2/3 of a pi. So I'm going to say the length would be 4 ticks, and that's a coincidence. That was the same on both. Don't go from here to 2/3 of a pi. It's from the phase shift. So from the phase shift, 4 ticks. Right? And I can mark the end of the period right there. And then if I want, I have room for another one. So there's 2 boxes, 2 cosine graphs, or cosine periods I can mark in there. So I've done pretty much everything. I've taken care of all these values. What's left? Negative cosine x. And what does a negative cosine x do? Instead of starting high and dipping down and ending high, it starts low and goes up and then goes back to low. So if I'm going to start low, say down here, and then I'm going to go up and back down, I'm going to end low. Well, where would I be at the high spot? In the middle of that. And if I've got to go from here to there and then back down, where do you think I cross the D line? Not there, but where? In the middles. Right there. And then try to avoid the Charlie Brown t-shirt zigzag. Right? I usually do this. Like, go ahead and mark all your points. You're just oscillating up and down at this point. And then go ahead and just kind of, you don't even have to start there. Just say, all right, bump up, bump down, bump up, and then half a bump down, half a bump down. But if you have your points in there and you give me the dreaded zigzag, I'm probably not counting off, although I'm marginally disappointed in your artistry. It's probably not going to affect anything because I get it. I mean, my wife's an artist. She can draw beautiful things. I cannot. I can do some level of creative stuff, but not like she does. You tracking with me? Okay, not so bad. Now remember, this time through, no open notes. You've got to know this stuff. So I've got 7 minutes. What I want to do is start you on a tangent and then show you the subtle differences. Now the major difference is it's just a completely different looking graph. Okay? And the box that you make isn't actually going to be a box. I call it a ladder. Okay? So let me get rid of this. Let me just talk about it. But a lot of it's similar. I mean, a lot of it. But there's enough different that's going to annoy you, and that's where people miss a lot of points, is on tangent, cotangent stuff, if they don't know their stuff. Hopefully you will. Now, walk me through it. If I have a tangent graph like this, okay? Now check it out. The D value, exactly the same. You come in here, you mark the D value, wherever it is. All right, same D. A value. Now, it's different in that it's not a ceiling on the graph because tangent goes up forever. But it is something that we use. So I'm still going to mark it the same way. I'm going to go up A, say that was A, and down A. So I'm going to still mark it the same way. Okay? Phase shift. Same thing in terms of finding it. So phase shift, you're still going to set that equal to 0, and you'll eventually get C over B. Go and mark that. Now here's where it's different. You'll notice that the phase shift right here, it's not the beginning of the period, is it? On all of my other graphs, the phase shift was where I went over. It was where I began the period. Now the phase shift is where? Right dead in the middle of the period. Are y'all with me on that? Now that's only true for tangent. Cotangent, phase shift, back at the beginning of the period. So phase shift is always the beginning of the period, except with tangent, which is extremely annoying. Now if you want, I can make it not annoying and say, hey guys, here's your tangent graph. But nobody wants to think about that as a tangent graph. They would rather think about this as a tangent graph. But if I thought about this as a tangent graph, then there's the phase shift at the beginning. But nobody thinks that way. So people like to think about tangent, cotangent like that. There should be a teacher who did the tan dance. Like your oldest sister had. Yeah, I didn't teach Liza calculus. Or did I? How old is she?
25.
Maybe I did. Maybe I did. I know I taught her twice. Anyway, there's a woman who used to teach here named Miss Morgan, and she was like really loud. Like, I mean, she was always like, woohoo! I mean, the first week, people would come back to my room and they're like, oh dear God, what have I gotten into? And then they'd get used to her, and it was like business. But she would always have a dance for everything. And one was the tan dance. I will not do the tan dance for you. I should have videoed it, but it was like, you can imagine, it was like, it had some of this, and it had some of this, but then a lot of dancing. And she was just a funny woman. She was a good teacher, but she was really funny. Anyway, you got to remember that's a major difference. The phase shift is in the middle. So what you do is you still mark it, but don't mark it with a vertical line, because you'll confuse that vertical line with a vertical asymptote, and it's not. So I usually mark the phase shift on tangent with just an arrow and say, there it is, because I'm going to use it to help me mark off what I call my ladder. Now, how do I use it? Well, then I go find period. Now, here's the second difference. The period is no longer 2 pi over b. You can complete an entire period of tangent and cotangent, not in 2 pi over b, but in pi over b. So the period's a little shorter. Okay? Now, here's where this plays out. Once you find the length of the period, instead of going from your phase shift over one period like we've been doing, what do you think we do if the phase shift's in the middle? How do I mark off the period if the phase shift's in the middle? If this is one period, from here to here, and the phase shift's in the middle, how do you think I mark it off? Half each way. That's right. So when you find that period, you go half that way, half that way. Are you seeing this? Now, once you've done that, you have the left side asymptote, that's an asymptote, the right asymptote, you have the middle line, you have the amplitudes, and what do you see right here? A fairly weak ladder. I hope you can get up wherever you're going in 3 rungs, but that's all you have. And once you have that, it's really easy to graph a tangent. A positive, like you're always going to have a point in the middle, whether your ladder looks like this, like this, like this, like this. Look, they all have that point right in the middle. But, as you all know when you go to the beach, it is all right to be tan. I would not know this, but it is all right, right? So tan goes to the right. It's all right to be tan if it's positive. Now, if it's negative, it switches directions. And then for cotangent, I used to have this, we would just say it goes the other way. And you might remember me saying this last year, but there was this kid, he goes, I got, no, you know how when you get to camp and you're like really late and you get the only cot left? And I was like, yeah, that's pretty creative. And this kid goes, that's stupid, man. It's all left to be caught is much better. We're like, that's the dumbest thing ever. But it stuck. So everybody's like, it's all right to be tan. It's all left to be caught. I don't even know what that means. But it's actually Sonny Farron's older brother, so that if you know Sonny. Are y'all with me? So I haven't graphed a tangent. We'll pick on that right when we get up on Monday, and then we'll be able to get through tangent, cotangent, and then knock out secant, cosecant. Y'all have a great weekend.